Hello, I'm Cyrin, and I will be presenting the results from a recent paper, Precise Limits on Charge-2 by 3 U1 Leptoquark. Please note that I'll be talking about only a subset of the results from the paper, and if anyone is interested to read more, the archive reference number is given right next to the heading of the poster in the next page. Okay, let's start with the motivation for the study. The Standard Model of Particle Physics, or SM in short, is an amazingly accurate theory describing all of the fundamental forces except gravity, but it is not without its limitations. There are some experimental measures that cannot be explained by the SM. They are anomalous and are called anomalies in short. These anomalies, among many other factors, stand as motivating factors for theories beyond Standard Model or BSM theories. When we talk about hypothetical particle, we generally are talking about particles described in the BSM theories. One such class of anomalies come from the measurements of a particle called B meson decaying to particles like muons, electrons, or tauons, collectively leptons. Two of these anomalies are RD and RD star. The predictions for the standard model and the actual measurement for these anomalies deviate from each other at about 3 sigma after a number of runs of data taking and multiple experiments. This is where the leptoquark comes in. The leptoquarks have been proposed in many BSM theories. They can also contribute to this decay if the beta meson decays via an intermediate leptoquark. In order to explain these anomalies, we need a leptoquark that couples to a B quark and a tau, that is a third generation quark and a third generation lepton, sorry, and couples to a C quark and a neutrino, that is a second generation quark. We take the first coupling as lambda 33L and the second one as a lambda 23L. The U1 leptoquark is a valid candidate for this anomaly in order to account for this anomaly, and we study these couplings of U1 in this study. So the main objective is to recast the LHC search data. The recasting is a process of interpreting a particular search data in terms of another. So what we are trying to do is that we are looking at the data taken by Atlas detector at the LHC in the tau tau channel when it was searching for a C prime, another hypothetical particle. And so in order to recast, we have to identify all such final states in the U1 processes that give us tau tau or whatever particular channel we are studying. Here it is tau tau. So uh, if you look at figure 1, you can see that we have considered plenty of processes that would yield final states at tau, and tau nu has been considered also in the actual paper. That is why you see a tau nu here. So when you consider plenty of leptoquark masses, say zero 0.5 to 3 TeV, if you look at the x-axis of figure 1, we are basically sorry, putting bounds on the parameter space lambda and the mass of leptoquark. So it's a 2D parameter space. We calculate what values or what points in this 2D are excluded or included by this LHC data. So how do we go about doing this? We start by implementing a model with the U1 and its relevant couplings in it. So we start with standard model and we add on the couplings, the relevant terms for U1, and make it a combined BSM model. Um, we consider each couplings individually. That means that when we study one, we switch off the other. That is how the scenarios have been described in the paper. RK, there are some names which are not important. So the MADGRAPH 5 is used to generate the required events. So MADGRAPH is a simulator that simulates the proton-proton collisions just like in LHC. And Pythia is a software that takes it from protons and the actual final state tauons, and the Delphis is actually the detector environment simulator. So basically you put uh, there are plenty of detectors at LSC, CMS, Atlas. So Delphis has a card for each of them. So if you want to analyze how the data would look like in an Atlas setting, there is a particular order of arranging the apparatus, the simulated apparatus, in order to get Atlas results, CMS results. So here we want to put it at the Atlas setting. The events are tagged using root software for tau tau channels. So the output of the DILFS is actually a lot of events relevant to our Tau Tau channel. Even then, the actual study, uh, which we are trying to recast to, we have to replicate that. So they might have a particular cut on the momentum of a particular particle, or a particular region in which they were looking at. So we have to implement that. That is where the root software comes in. We fit our model on the existing LSC search data of Tau Tau, then perform a simple chi-square test for checking the goodness of the fit. So this fitting is done by combining all the relevant final states with 2 tau systematically. We know, or we estimate how they depend on lambda, the particular lambda, whatever we are considering it in a particular scenario, and we take care of that before combining each of the process contribution. So the lambda is the independent parameter um, that we check for chi-square. So what do we get out of all this? Um, the first plot is actually called the exclusion plot. We call it the exclusion plot because anything above the line is actually excluded for this particular lambda value. So for example, LHC, the limits obtained from the LHC data says that for a 2 TeV leptoquark, it cannot have a lambda 2,3L coupling more than zero point 0.8 and 3,3L coupling more than 1.7. So that's how you read this um, plot. And considering the individual scenarios where we set lambda uh, 2 3l and the other as 0, or 3 3l and the other as 0, we only look at one particular coupling. We plot the allowed regions which comes from flavor physics in the same plot to see that how how strong are our limits. Are the allowed regions um, excluded or included? So we check that the yellow region is actually the RD star allowed regions that come from um, the flavor data. So as you can see in the lambda 23L alone case, it is completely ruled out. It is in the excluded region. So what it says is that a model cannot exist with just lambda 23L and explain RD star. But when you come to the lambda 33L case, the model, the blue line is actually the line from the exclusion plot. So it actually shows that there is some considerable parameter space that is actually allowed and below that line. So lambda C3L alone models could still work. So for completeness sake, we actually check um, lambda 2,3L and 3,3L combined a little bit. So lambda 2,3L is allowed to vary, but 3,3L is fixed as zero point 0.5. So then you get the exclusion limits as uh, the lines change a little bit, and you can see the RD star is completely and well accommodated in the allowed region. So what we can conclude is that in the minimal scenarios where we select only one coupling as 1 and the other as 0, almost all of RD star favorable regions are excluded except for a small case in 33L. But when you combine the parameter space, even for a small like a, a value like zero point 0.5 for one lambda, you can actually get allowed favorable regions. So there are more plots in the actual paper if you want to go through them. Um, that's it for this poster. Thanks.